sloppy quorums and hinted handoff. Databases with appropriately configured quorums can tolerate the failure of individual nodes without the need for failover. They can also tolerate individual nodes going slow, because requests don't have to wait for all N nodes to respond. They can return when W or R nodes have responded. These characteristics make databases with leaderless replication appealing for use cases that require high availability and low latency, and that can tolerate occasional stale reads. However, quorums as described so far are not as fault-tolerant as they could be. A network interruption can easily cut off a client from a large number of database nodes. Although those nodes are alive, and other clients may be able to connect to them, to a client that is cut off from the database nodes, they might as well be dead. In this situation, it's likely that fewer than W or R reachable nodes remain, so the client can no longer reach a quorum. In a large cluster with significantly more than N nodes, it's likely that the client can connect to some database nodes during the network interruption, just not to the nodes that it needs to assemble a quorum for a particular value. In that case, database designers face a trade-off. Is it better to return errors to all requests for which we cannot reach a quorum of W or R nodes? Or should we accept writes anyway, and write them to some nodes that are reachable but aren't among the N nodes on which the value usually lies? The latter is known as a sloppy quorum. Writes and reads still require W and R successful responses, but those may include nodes that are not among the designated N home nodes for a value. By analogy, if you lock yourself out of your house, you may knock on the neighbor's door and ask whether you may stay on their couch temporarily. Once the network interruption is fixed, any writes that one node temporarily accepted on behalf of another node are sent to the appropriate home nodes. This is called hinted handoff. Once you find the keys to your house again, your neighbor politely asks you to get off their couch and go home. Sloppy quorums are particularly useful for increasing write availability. As long as any W nodes are available, the database can accept writes. However, this means that even when W plus Rn, you cannot be sure to read the latest value for a key, because the latest value may have been temporarily written to some nodes outside of N. Thus, a sloppy quorum actually isn't a quorum at all in the traditional sense. It's only an assurance of durability, namely that the data is stored on W nodes somewhere. There is no guarantee that a read of R nodes will see it until the hinted handoff has completed. Sloppy quorums are optional in all common Dynamo implementations. In Rike they are enabled by default, and in Cassandra and Voldemort they are disabled by default. We previously discussed cross-data center replication as a use case for multi-leader replication. See multi-leader replication on page 168. Leaderless replication is also suitable for multi-data center operation, since it is designed to tolerate conflicting concurrent writes, network interruptions, and latency spikes. Cassandra and Voldemort implement their multi-data center support within the normal leaderless model. The number of replicas N includes nodes in all data centers, and in the configuration you can specify how many of the N replicas you want to have in each data center. Each write from a client is sent to all replicas, regardless of data center, but the client usually only waits for acknowledgement from a quorum of nodes within its local data center so that it is unaffected by delays and interruptions on the cross-data center link. The higher latency writes to other data centers are often configured to happen asynchronously, although there is some flexibility in the configuration. Rike keeps all communication between clients and database nodes local to one data center, so N describes the number of replicas within one data center. Cross-data center replication between database clusters happens asynchronously in the background, in a style that is similar to multi-leader replication. Detecting concurrent writes. Dynamo-style databases allow several clients to concurrently write to the same key, which means that conflicts will occur even if strict quorums are used. The situation is similar to multi-leader replication. See handling write conflicts on page 171. Although in Dynamo-style databases conflicts can also arise during read repair or hinted handoff. The problem is that events may arrive in a different order at different nodes, due to variable network delays and partial failures. For example, Figure 5-12 shows two clients, A and B, simultaneously writing to a key X in a 3-node data store. Figure 5-12. Concurrent writes in a Dynamo-style data store. There is no well-defined ordering. Node 1 receives the write from A, but never receives the write from B due to a transient outage. Node 2 first receives the write from A, then the write from B. Node 3 first receives the write from B, then the write from A. If each node simply overwrote the value for a key whenever it received a write request from a client, the nodes would become permanently inconsistent, as shown by the final GET request in Figure 5-12. Node 2 thinks that the final value of x is b, whereas the other nodes think that the value is a. In order to become eventually consistent, the replicas should converge toward the same value. How do they do that? One might hope that replicated databases would handle this automatically, but unfortunately most implementations are quite poor. If you want to avoid losing data, you, the application developer, need to know a lot about the internals of your database's conflict handling. We briefly touched on some techniques for conflict resolution in handling write conflicts on page 171. Before we wrap up this chapter, let's explore the issue in a bit more detail. Last write wins. Discarding concurrent writes. One approach for achieving eventual convergence is to declare that each replica need only store the most recent value and allow older values to be overwritten and discarded. Then, as long as we have some way of unambiguously determining which write is more recent, and every write is eventually copied to every replica, the replicas will eventually converge to the same value. As indicated by the quotes around recent, this idea is actually quite misleading. In the example of Figure 5-12, neither client knew about the other one when it sent its write requests to the database nodes, so it's not clear which one happened first. In fact, it doesn't really make sense to say that either happened first. We say the writes are concurrent, so their order is undefined. Even though the writes don't have a natural ordering, we can force an arbitrary order on them. For example, we can attach a timestamp to each write, pick the biggest timestamp as the most recent, and discard any writes with an earlier timestamp. This conflict resolution algorithm, called Last Write Wins LWW, is the only supported conflict resolution method in Cassandra and an optional feature in RIAC. LWW achieves the goal of eventual convergence, but at the cost of durability. If there are several concurrent writes to the same key, even if they were all reported as successful to the client because they were written to W replicas, only one of the writes will survive and the others will be silently discarded. Moreover, LWW may even drop writes that are not concurrent, as we shall discuss in timestamps for ordering events on page 291. There are some situations, such as caching, in which lost writes are perhaps acceptable. If losing data is not acceptable, LWW is a poor choice for conflict resolution. The only safe way of using a database with LWW is to ensure that a key is only written once and thereafter treated as immutable, thus avoiding any concurrent updates to the same key. For example, a recommended way of using Cassandra is to use a UUID as the key, thus giving each write operation a unique key. The happens before relationship and concurrency. How do we decide whether two operations are concurrent or not? To develop an intuition, let's look at some examples. In Figure 5-9, the two writes are not concurrent. A's insert happens before B's increment, because the value incremented by B is the value inserted by A. In other words, B's operation builds upon A's operation, so B's operation must have happened later. We also say that B is causally dependent on A. On the other hand, the two writes in Figure 5-12 are concurrent. When each client starts the operation, it does not know that another client is also performing an operation on the same key. Thus, there is no causal dependency between the operations. An operation A happens before another operation B if B knows about A, or depends on A, or builds upon A in some way. Whether one operation happens before another operation is the key to defining what concurrency means. In fact, we can simply say that two operations are concurrent if neither happens before the other, i.e. neither knows about the other. Thus, whenever you have two operations A and B, there are three possibilities. Either A happened before B, or B happened before A, or A and B are concurrent. What we need is an algorithm to tell us whether two operations are concurrent or not. If one operation happened before another, the later operation should overwrite the earlier operation, but if the operations are concurrent, we have a conflict that needs to be resolved. Concurrency, time, and relativity. It may seem that two operations should be called concurrent if they occur at the same time, but in fact, it is not important whether they literally overlap in time. Because of problems with clocks in distributed systems, it is actually quite difficult to tell whether two things happened at exactly the same time, an issue we will discuss in more detail in Chapter 8. For defining concurrency, exact time doesn't matter. We simply call two operations concurrent if they are both unaware of each other, regardless of the physical time at which they occurred. People sometimes make a connection between this principle and the special theory of relativity in physics, which introduced the idea that information cannot travel faster than the speed of light. Consequently, Two events that occur some distance apart cannot possibly affect each other if the time between the events is shorter than the time it takes light to travel the distance between them. In computer systems, two operations might be concurrent even though the speed of light would in principle have allowed one operation to affect the other. For example, if the network was slow or interrupted at the time, two operations can occur some time apart and still be concurrent, because the network problems prevented one operation from being able to know about the other. Capturing the happens before relationship, let's look at an algorithm that determines whether two operations are concurrent or whether one happened before another. To keep things simple, let's start with a database that has only one replica. Once we have worked out how to do this on a single replica, we can generalize the approach to a leaderless database with multiple replicas. Client 1 adds milk to the cart. This is the first write to that key, so the server successfully stores it and assigns it version 1. The server also echoes the value back to the client, along with the version number. Client 2 adds eggs to the cart. Not knowing that Client 1 concurrently added milk, Client 2 thought that its eggs were the only item in the cart. The server assigns version 2 to this write and stores eggs and milk as two separate values. It then returns both values to the client, along with the version number of 2. Client 1, oblivious to Client 2 write, wants to add flour to the cart, so it thinks the current cart contents should be milk, flour. It sends this value to the server, along with the version number 1 that the server gave Client 1 previously. The server can tell from the version number that the write of milk, flour supersedes the prior value of milk, but that it is concurrent with eggs. Thus, the server assigns version 3 to milk, flour, overwrites the version 1 value milk, but keeps the version 2 value eggs and returns both remaining values to the client. Meanwhile, Client 2 wants to add ham to the cart, unaware that Client 1 just added flour. Client 2 received the two values milk and eggs from the server in the last response, so the client now merges those values and adds ham to form a new value, eggs, milk, ham. It sends that value to the server, along with the previous version number 2. The server detects that version 2 overwrites eggs, but is concurrent with milk, flour, so the two remaining values are milk, flour with version 3, and eggs, milk, ham with version 4. Finally, Client 1 wants to add bacon. It previously received milk, flour, and eggs from the server at version 3, so it merges those, adds bacon, and sends the final value milk, flour, eggs, bacon to the server, along with the version number 3. This overwrites milk, flour. Note that eggs was already overwritten in the last step but is concurrent with eggs, milk, ham, so the server keeps those two concurrent values. The data flow between the operations in Figure 5-13 is illustrated graphically in Figure 5-14. The arrows indicate which operation happened before which other operation, in the sense that the later operation knew about or depended on the earlier one. In this example, the clients are never fully up to date with the data on the server, since there is always another operation going on concurrently, but old versions of the value do get overwritten eventually, and no writes are lost. Figure 5-14. Graph of causal dependencies in Figure 5-13. Note that the server can determine whether two operations are concurrent by looking at the version numbers. It does not need to interpret the value itself, so the value could be any data structure. The algorithm works as follows. The server maintains a version number for every key, increments the version number every time that key is written, and stores the new version number along with the value written. When a client reads a key, the server returns all values that have not been overwritten, as well as the latest version number. A client must read a key before writing. When a client writes a key, it must include the version number from the prior read, and it must merge together all values that it received in the prior read. The response from a write request can be like a read, returning all current values, which allows us to chain several writes like in the shopping cart example. When the server receives a write with a particular version number, it can overwrite all values with that version number or below since it knows that they have been merged into the new value, but it must keep all values with a higher version number because those values are concurrent with the incoming write. When a write includes the version number from a prior read, that tells us which previous state the write is based on. If you make a write without including a version number, it is concurrent with all other writes, so it will not overwrite anything. It will just be returned as one of the values on subsequent reads. This algorithm ensures that no data is silently dropped, but it unfortunately requires that the clients do some extra work. If several operations happen concurrently, clients have to clean up afterward by merging the concurrently written values. Raya calls these concurrent values siblings. Merging sibling values is essentially the same problem as conflict resolution in multi-leader replication, which we discussed previously. See Handling Write Conflicts on page 171. A simple approach is to just pick one of the values based on a version number or timestamp. Last write wins, but that implies losing data. So, you may need to do something more intelligent in application code. With the example of a shopping cart, a reasonable approach to merging siblings is to just take the union. In Figure 5-14, the two final siblings are milk, flour, eggs, bacon and eggs, milk, ham. Note that milk and eggs appear in both, even though they were each only written once. The merged value might be something like milk, flour, eggs, bacon, ham, without duplicates. However, if you want to allow people to also remove things from their carts, and not just add things, then taking the union of siblings may not yield the right result. If you merge two sibling carts and an item has been removed in only one of them, then the removed item will reappear in the union of the siblings. To prevent this problem, an item cannot simply be deleted from the database when it is removed. Instead, the system must leave a marker with an appropriate version number to indicate that the item has been removed when merging siblings. Such a deletion marker is known as a tombstone. We previously saw tombstones in the context of log compaction in hash indexes on page 72. As merging siblings in application code is complex and error-prone, there are some efforts to design data structures that can perform this merging automatically, as discussed in Automatic Conflict Resolution on page 174. For example, RIAC's data types support uses a family of data structures called CRDT that can automatically merge siblings in sensible ways, including preserving deletions. The example in Figure 5-13 used only a single replica. How does the algorithm change when there are multiple replicas, but no leader? The collection of version numbers from all the replicas is called a version vector. A few variants of this idea are in use, but the most interesting is probably the dotted version vector, which is used in RIAC 2.0. We won't go into the details, but the way it works is quite similar to what we saw in our cart example. Like the version numbers in Figure 5-13, version vectors are sent from the database replicas to clients when values are read, and need to be sent back to the database when a value is subsequently written. RIAC encodes the version vector as a string that it calls causal context. The version vector allows the database to distinguish between overwrites and concurrent writes. Also, like in the single replica example, the application may need to merge siblings. The version vector structure ensures that it is safe to read from one replica and subsequently write back to another replica. Doing so may result in siblings being created, but no data is lost as long as siblings are merged correctly. A version vector is sometimes also called a vector clock, even though they are not quite the same. The difference is subtle. Please see the references for details. In brief, when comparing the state of replicas, version vectors are the right data structure to use.